Guys, I'm Jitimarthi, and in this video, I'm here to discuss about the statistical mechanics that we often study in the graduation and post-graduation period. So, I'm not going to derive anything in this particular video. I'm only here to give an overall idea about what is statistical mechanics and why should we consider that. And also we will try to solve some problems based on this thing. So before we are starting about statistical mechanics, we should know the base or the root of this particular subject, that is thermodynamics. So what is thermodynamics? It's a study which is related with exchange of heat energy or any other particular source of energy. So we can say that thermodynamics is the study related to energy transfer. So, if you guys are a good observer, we can see that everything in this particular nature is a thermodynamic system. And I will define the word system. System is something that we scientists or researchers put our efforts to investigate. So whatever area or region that is put under investigation is called as a system, and everything else that will externally depend on this particular system's characteristics are known as the surroundings. So everything in this nature is a thermodynamic system. That is, this energy and matter is being transferred between the system and surroundings. So we have a basic idea about what is system and surrounding. So there are three types of systems. That is an isolated system, open system, and closed system. From the word isolated, we can say that this particular system will not transfer energy or matter with the surrounding. And in the case of an closed system, it will only transfer energy between the surroundings and not the matter. That is, when we boil a particular glass of water and we close the container's upper part, it will only transfer heat energy to the surrounding, and the matter will be inside the container. And the third system is the open system, where both energy and also matter is being transferred between the surroundings. So we have a basic idea what is thermodynamics. So why should we consider statistical mechanics? From the name itself, we can say that statistical mechanics, statistics, is a study of a system in equilibrium, where the system has equilibrium energy with the surrounding. So, with the earlier example, I said about a glass of water or a water in boiling condition. When the heat is turned off, that particular system will be in equilibrium after some amount of time with the surrounding. So, this statistical mechanics will only consider about the systems in equilibrium. So, basically, we can subdivide this statistical mechanics into two main categories, that is classical and quantum. So, in what basis we are classifying them as classical and quantum? Every macroscopic system can be classified into classical and quantum based on the properties. Like in the case of classical system, the particles are macroscopic and they are identical and distinguishable. That is the property of a classical particle. Distinguishable. and in the quantum case, they are indistinguishable. You can then subdivide this quantum into take that is bosons and fermions also. I will get into that later. But what's the main difference between both of these? In the classical system, a single particle or a group of particles can occupy any of the several cosmic states. That is, if you consider this lines are the states, there are several states, and the classically a single particle which is distinguishable and identical have the freedom to occupy any of the state, and they can only occupy only one state as they are distinguishable. And in the case of quantum, is exactly the opposite of that. In this case, a particular single quantum state can be occupied by several particles. If you consider this line as a state, quantum state, it can be occupied by several particles. More than one particle have the chance. It may occupy because based on fermions and bosons it may differ, but as they are indistinguishable particles, we can distinguish between any one of the particles. So all particles have equal chance of occupying a particular quantum state. So it's like the opposite of a classical statistical mechanics. So we said that statistical mechanics is with a system in equilibrium. So the aim of statistical mechanics is to derive all the equilibrium properties of macroscopic molecule system from the laws of molecular dynamics. So they are only focusing on that particular system and equilibrium state. And the statistical mechanics can be combined with our thermodynamics also, because thermodynamics is the root of the statistical mechanics. We said that there are three basic systems that are isolated, open and closed system. But when we come into statistical mechanics, we are not considering a system. We are grouping this cluster of microstates into a group known as ensembles. So ensembles, I will give the definition. Ensemble is a cluster of mental copies of all such macrostates which correspond to the same macrostate. So it's a cluster of copies. So based on that, we can classify them into three types of ensembles. That is microcanonical ensemble, canonical ensemble, and grand canonical ensemble. So we can say there are three types of ensembles. That is microcanonical, canonical, and grand canonical. So how are they similar to thermodynamics? In what way they have thermodynamic factors? In this microcanonical system, we are considering the ensembles which are isolated, which does not transfer any matter or energy to surroundings. So we can consider this as an isolated system. In canonical, we are not isolating this particular system, but we are having the surrounding is giving an uniform temperature T to the system. So it will transfer energy to the surrounding. So we can call this as a closed system. And grand canonical, it is transfer or exchange both matter and energy to the surrounding. So we can call this as an open system. But in this particular statistical mechanics, we are dealing with these systems in an equilibrium state. So we have seen that what is statistical mechanics. So now is the quantum statistical mechanics. So the classical statistical mechanics, these particles are distinguishable, and so that they can occupy, they have chance of occupying more than one state. So quantum statistical mechanics, we can define that an observer of a system is associated with a Hermitian operator which operates on Hilbert space. So in quantum statistical mechanics, the space that they are considering is a Hilbert space. So as I said, I am going to do any derivations in this area. Now we can classify the particles based on three statistics. That is, any cluster of quantum particles can be classified based on Maxwell-Borsell's distribution, Fermi-Dirac and Bose-Einstein distribution. So on the basis of this, we can classify the matter or particles. So I would like to pinpoint the difference between this classical particle that is following the Maxwell-Borsell and this quantum particle. So we can differentiate between both these three. First is the classical mechanics. I have not visible with this classical particles. And here is the quantum. Quantum we have divided into two types, as bosons and fermions. We will discuss what is bosons and what are fermions in this furthermore. So the basic difference, as I said in the beginning, is that classical particles are identical and distinguishable. Bosons, in the case, they are quantum particles, so they are identical and indistinguishable. And fermions, they are also, as quantum particles, they are identical and indistinguishable. So the basic concepts that we have discussed earlier. And we said that these three obey three statistics. The first one is classical particle, they obey the Maxwell-Borsell's statistics. And second one, bosons. They obey the Bose-Einstein. From the name you can say it obey the Bose-Einstein statistics. And third one, fermions. These are a particular type of particles that won't entertain others in their particular energy area. So we can discuss that. So they obey the Fermi-Dirac statistics. So that's the speciality with this fermions. The thing is that as they obey the Pauli's exclusion principle, only a single fermion can occupy one energy state. So that's the peculiarity with these fermions. So they obey the Pauli's exclusion principle. In the case of bosons, they won't obey the Pauli's exclusion principle. That is, in any number of particles have equal probability of occupying a particular state. Did you see obey the Pauli's exclusion principle? Now we can consider about the spins. In the case of classical, they can have any number of spins, because if we consider a gas molecule system, they have particles having any kind of spins. So they can have any kind of spins. But when we are looking for the bosons, the particles are having an integral spin. In the case of fermions, they can only have half integral speed. Now, so we have said about the difference between these particles. So, what are the particles? In the case of classical, we can say that most of the metals, classicals, as gas molecules, etc., can be example of this classical. In the case of bosons, these are like energy carriers. So, if we consider in the case of a light coming from a distant source, that is, they come as a quantum resonance photons. So they are energy carriers, and these energy carriers are the examples of bosons. They obey the Bose-Einstein statistics. So examples are, all the energy carriers are examples like photons, phonons, and theoretically we can say gravitons also, but it's not, practically it's not being proved, right? But theoretically it's proved. Gravitons, etc. are bosonic particles. And fermions. The fermionic particles are the fundamental particles. We know that the fundamental particles like quarks, electrons. These particles are known as the fermions. But these particles do not allow another identical substance to be in the particular energy level. And the examples are the fundamental particles, electrons, quarks, etc. You know, quarks, they are the fundamental particles that in the proton. There are 3 quarks in protons, and electrons the fundamental particle. So this is the basic differentiation between these 3 particles, that is classical and bosonic and fermionic particles. So we have learned about what are their differentiations. I will wait, but it cannot be, theory cannot be completed without a problem. So we are learning this all theories for practical application. So we can discuss a problem based on the theories that we have learned till now. So I have written 2 problems that are very simple problems that could be understood by all of the viewers. The first problem I will just read out. You are given a system of 2 identical particles which may occupy any of 3 energy levels given by energy is equal to n epsilon. Now n can be 0, 1 and 2. The lowest energy level is doubly degenerate and the system is in a thermal equilibrium at temperature T. So our aim is to identify the configuration, partition function and internal energy in the case of fermions, boson and classical particles. So we can apply all the theories that we have learned now in this particular program. So first I am going to identify the configuration of a classical particle. So these particles obey what? They obey the Maxwell-Boltzmann configuration. So we can draw out the energy levels. There are 3 energy levels, but it is saying that the lowest energy level is doubly degenerate. So in this quantum level, our classical level, quantum statistical mechanics, the difference is that we are also discussing about the degeneracies in the energy level. So the lowest energy level is doubly degenerate. So we can draw 2 levels that are close to each other. This level is close when is equal to 0. Is equal to 1, is equal to 2. So our aim is that the energy is A is equal to n epsilon, and we just find out what are configuration that can be possible. It's better to draw in a so here we are going to apply the concepts. The first concept is that classical particles are identical and distinguishable. So we can say these particles in classical, let us know that A and B, as they are distinguishable. So we are going to occupy all the levels. So first possibility is that this A and this B. Second possibility is that the reverse order, because both are distinguishable and identical. A, B. Third possibility is that let us use next is that and opposite. I hope you are listening with that. So as there are distinguishable, we can both do in both the ways that A can occupy here and B can occupy here and A can occupy here. Both different directions we can do. That way there will be a very about 16 states there will be. And as they are not obeying the Congress exclusion principle, two particles can occupy the same energy level. So we can have this possibility also. AB in 1, AB also in 2. So there are about, you can just mark it down. So there are about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11,